And I was told, don't dwell on FT8. Don't dwell on FT8. Don't dwell on FT8. You know. So that's my end of the hardware. You can get into it with a little $3 USB, sound card, and you can have fun. You can use your laptop audio direct. Try that. Just have to wait to connect the radio and the computer. So how do sound cards work? Well, it's just audio, right? Dee-dee-dee-dee-dee-dee. So we can send that audio into a radio, and we've got to modulate the carrier, right? Modulate means send some information. So the traditional ways we can modify a carrier wave for information is change the amplitude, AM, change the frequency, FM, change the phase, PM. So I want to go into a little bit about each of these three. It's not so obvious, maybe. So if I have some signal, so here's just the sine wave signal, or I've got a microphone and I'm going, something, simple audio signal. And if I frequency modulate it, what does that mean? It means when you've got more audio, the deviation becomes, here the waves are crowded together, so the frequency went up. And over here, the frequency is, the waves are getting spread out, so the frequency is what? Decreasing. So I'm frequency modulating the signal. Notice, what about the amplitude here? Oh, an FM signal traditionally has a constant amplitude. That's interesting, especially when we get into sound card modes. Now that's true if the modulation audio goes into a single sideband radio, but I'm using a mode like AFSK RTTY. If I look at my power meter on the radio, but my radio's in single sideband, on RTTY it says 50 watts, 50 watts, 50 watts. Now if I talk and I'm on AM, the power goes up and down. So amplitude modulation, as the envelope goes up and down, the amplitude, that means the power output of the signal's changing. Obviously, if you've operated single sideband, you know that. If you talk louder, you get more power. That's why we talk loud, to get DX. Hey, hey, hey. So the same with the digital mode, except it's, it's analog sound from a sound card rather than, human voice. So the important thing, I'm going to come back to this, FM constant amplitude. That has some implications down the line. So how do we send data, digital mode? How do we send data by using AM, FM, or PM? So let's take a look at this. So if I'm sending zeros and ones, here's a representation. Maybe the 0 means there's no RF carrier. That means nothing, right? The radio is not transmitting anything. And if I have a 1, suddenly the signal comes up, and it's a constant power. Look, constant power. Another 0, the power goes off. So the amplitude shift is really, it's obviously like CW. There's radio frequency or no radio frequency. I'm not changing the frequency. I'm not changing the phase. I'm just changing the amplitude. My frequency is fixed. Though typically, we say that's like CW. Frequency shift. Well, that's the RTTY. Zeros are one frequency, okay, and the ones are a different frequency. D, 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 D. Notice here, the amplitude's constant, right? But also notice, hey, wait a minute, the radio's never off. So folks realized this when they were on RTTY. You might burn up your amplifier because it's never time to breathe. It's just always full power, full power. So you have to watch out on these older radios that had RTTY. Often the instruction manual said, this is a, what's the phrase? Continuous output, I forget. High duty cycle, something like that. Means it's always on. So you're not running and jogging and walking and running. You're always running. So you want to watch that, it's not 100 watts for 10 minutes on radio. You burn up your finals. Phase shift. This is a little trickier. I had a long discussion about 10 years ago with the author of PSK 31. What is phase shift? How do you do it? So the zeros and the ones might be a phase shift, and the zeros might be no phase shift. But look, how do you show a phase shift on a sine wave here? It's just the timing. So think of phase as the timing. I'm going to come back and show you what that means. It's a little harder to describe it. PSK 31 is one of these, and I'll show you how that works. So the typical modes that you hear today have to be either an AM, an FM, or a PM, or some combination. So what do AM and CW have in common? Think about that for a minute. What do the modes Olivia, THOR, MFSK, and FT8, what do they all have in common? I didn't play an FT8, but I think you know what that sounds like. What do those modes all share in common? And how about PSK and Vera? 8PSK, MT63, what do those share in common? So normally I'd stop and ask you guys to talk, but we can't do that tonight. So AM and CW are amplitude shift. I mean AM, amplitude modulation. CW is an amplitude shift in AM mode. CW is double sideband AM. It's just the carriers going on and off, on and off, on and off. So CW, yes, CW is AM. RTTY, Olivia, THOR, they're all frequency shifts. D, 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 you know, whether it's 2 tones or 100 tones. They're just shifting the frequency. And PSK and Vera and these others, they're all phase shifts. But the phase shift modes also shift their amplitude. And I'll show you why they have to do that. I don't want to really talk too much about the emission classifications, but, you know, like government agencies like to classify these. We used to say CW is A1A. So the A and the 1 and the A, they represent something, and this is another half-hour talk what all these mean. But it's a way the government can classify a type of an emission. So why do we want to use sound card digital modes? I thought about this when I was asked to do this talk, and I thought, well, you know, there's different purposes. I like to chat. I like to talk to people. So the chat modes or the image modes, I could send an image of something, my radio station. People share all kinds of weird images, and it's legal. We usually send them on something like 20 meters at one frequency, so we all know, oh yeah, that's the slow scan frequency, 14230 or 7041 or whatever it is. So they tend to hang around one frequency that can find each other. And it's just scanning the image, diddly, just like a fax machine. Or you can send a digital image. There's programs that can do that. So image and chat modes. The DX modes, well, there's your FT8, you know, FT4. If you go back 5 years, JT65, could work the moon bounce. CW, PSK, these are nice modes for just, you know, with a little bit of power and a dipole antenna, work the world. The contest modes, well, man, every weekend there's some contest somewhere. They're often RTTY. I never hear RTTY unless there's a RTTY contest. Then it's like, there's all these RTTY stations. CW, PSK 31, FD. These are good, you know, contest modes because what do you have to do on a contest? Yeah, 599 EPA. Thank you. Next. It's like kind of boring, but some people love to do contests. Emergency communication, the EMCOM modes. I've gotten more involved in this in the last 10 years of my life. So what's important here is accuracy, 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 and to some extent speed. So we don't pick up microphones when we're on ENCOM duty and start talking about what we need. And I certainly wouldn't get on CW with my CW skills to send emergency messages with CW at my stage of life. But the EMCOM modes, PATOR, great international emergency communication mode. Vera is a new sound card mode. Packet, well, Packet's been around for years and years. And the different HF modes, they're usually THOR and MFSK for emergency traffic. So I got a question once at the last one. What's the best mode? What's the best car? You know, what's the best language? You know, you tell me. What's your mode? What are you trying to accomplish? So when we talk about AM, we normally think of a voice. So typically a voice goes through an audio amp, mixes with a carrier, and you get an amplified modulated wave. The envelope follows whatever your voice is doing here. Well, we all know that works. With CW, now, what is CW? Continuous wave. Well, it's not, you know. So CW, the more proper description might be amplitude shift keying, ASK. Or dig up an old handbook and they're called OOK. OOK, what is that? On, off keying. Well, that's exactly what it is, isn't it? So why is this a digital mode? All right, so let's see here. So if my key is up, I'm not sending out anything. That's a 0. So a 0 means no RF. When I put the key down, suddenly I have RF. Now, at the other end, that RF is doing anything. But if the station who's listening has another little oscillator called a BFO, they hear bzzz, you know, a sound. So there's either no sound or sound. Now be careful here. I had an argument with a friend about this. Zeros and ones are not dits and das. I'm not sending dits and das. Well, I mean, I'd argue, yeah, I really am, but where's the silence? If a dit is 1 and a da is 0, like where's the silence? Dit, 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 you know. You've got to represent silence, so now you got to watch out here. So CW is binary because 0 is silence and a 1 is sound. So how do I differentiate dits and das? Oh, that's easy. The short sound is a dit, that's 1. The da, there's no space, right? The da is just 3 ones. So 3 ones isn't dit, dit, dit. We know that's S. It's da, da, but the timing is 1, 1, 1, 1, 1, 1. The standard is for DAs and DITs 3 to 1. But I work a lot of guys with hand keys, and they, you know, like sending CW da 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 da. You know, like I can hear what they're doing, but like that's not the right ratio of DITs and DAs. So 0 is silence, 1 is sound or RF. So and E is just 1, and I is 1 0 1 dit dit. You need the silence between the 1 and the 1. S, dit, dit, dit. H, dit, 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 dit. So if I want to send CW on a computer, I've got to start out with something like this. What's the T? The dash. Da. M, da, silence, da. O, da, silence, da, silence, da. Then the question is, well, when does one letter end and the next letter begin? So you need a longer space, longer silence between letters, and maybe even a longer silence between words, although rarely in CW do you do that. So you can make a longer silence by going 0, 0, 0, or 5 zeros, whatever you want. So that's the binary nature of CW. All right, so a little bit of CW. I know it's not a sound card necessarily mode, but we all try to, you know, learn how to send, well, most of us try to learn how to send CW with this. So our CW Morse key was doing something in here that turned the RF on and off. How about this? When I was a kid, I tried to use one of these, and I failed miserably. I learned to send CW with a hand key at about 25 words a minute. I was 12 years old, and I can still do that today. I can't copy CW at 10 words a minute. It's like nonsense. But if I hear CW at about 20 to 30 words a minute, I just close my eyes, and I almost don't listen for a letter. I listen for a word. So, you know, QTH, name, Bill, New York, whatever. If I miss a letter, you don't freak out. What's the whole word I'm looking for? But here, the dots go da 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 da, and the dashes go da, and then dag. The dashes aren't automatic, so I never mastered this. I found this on the internet. I thought, oh, this is just so cool. I got to throw in this picture. So you have a choice. Hand key. Look how beautifully this is machined. Or a paddle, you know, or this is the bug, so it's a mechanical thing here. Or just the, you know, the dots and dashes are like left and right stereo here. I love that picture. I don't have this. I'd love to. So when you're sending CW, the issue is how quickly does the RF come on and off? Is it clean, clear, well-sounding CW? So the rise time and the fall time are kind of critical. New radios are just really perfect about this, but the old rigs sounded pretty bad. I did work someone on 40 meters about 3 years ago, and man, key clicks everywhere. You know, and I worked one about 10 years ago, and the sound in my headphones was dwad it, dwad it, dwad, dwad it, dwad. And I thought, man, voltage regulation. QST publishes these sorts of things. What's the CW keying shape? So this was from, you know, ARRL. Look at the varieties of key. Now, when they do this test, they do it at like 60 words a minute. It's like I thought, I don't care what it's like at 60 words a minute. I care. What does it look like at 20 words a minute? But fascinating how some rigs have cleaner CW. Now, this is my SDRplay, and I was picking up W1AW, look, almost 50 over 9. My antenna was an 80-meter dipole. I could have heard them if I put my finger in the socket. Look at this CW signal. Whoa. So the question is, well, what's the bandwidth of W1AW? Well, that's a silly question. Where? You know, if I'm listening just here, the bandwidth is like 100 hertz. If I'm listening down here, 50 dB, it's like 300, 400, 500 hertz. So as you get to fainter and fainter, sounds here, the RF bandwidth increases. So it's tricky to say, isn't it? What's the CW bandwidth? But for a typical person listening with headphones, a couple hundred hertz. CW, well, here's CW during a contest on 40 meters. Again, my SDRplay. So here's 7 megahertz down here. Look, the first 25 kilohertz. 25 kilohertz, there's 2 signals. The expert part of the band, the extra part. What a wasted space here. Look at all these guys jammed in here, all, trying to get CW contacts. Frequency modulation. That's a little easier to show. Frequency modulation. A 0 is one frequency. A 1 is a different frequency. How different? Well, the software can decide. Notice there's no silence. That's important. On FM, the frequency is changing based on the modulation, whether it's a human voice or, a sound card sound. It's a constant amplitude, so your radio's always putting out the same power. So if I'm on 2 meters, and I've heard people say this, I'm on 2 meters, you don't hear me very well. Okay. So if I shout, do I get more power? No. Get more deviation maybe, but not more power. So in these FM modes, you can be a little sloppier with the amplifier. 0 and a 1. One frequency, another frequency. So the common one is RTTY, because RTTY is just 2 tones. D, 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 D. Radios could generate RTTY by 2 techniques. The radio might have a RTTY operating generator, which means you send a data pulse, not sound. You send a data pulse to the radio on 1 jack, and it moves the VFO up by 170 hertz. There's a little capacitor or something in there. D, 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 D. So it's data pulses. So they call that direct FSK. Most of it just call it RTTY. Frequency shift key. The other way, and it's much simpler, and actually most of us do it this way, what if I go D, 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 D in a sound card? That's really easy to do because my computer has a sound card. So I generate the RTTY tones in sound waves. Well, voltages. Now, what if I feed those into a microphone jack of a single sideband radio? The single sideband radio, just like my human voice, it moves that to a radio frequency depending on my VFO. So what comes out of the radio? D, 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 on some radio frequency, an RF wave. So the audio gets converted to radio shifting in the radio. You might say my transmitter is an up converter. It's up converting audio to RF. That's all it's doing. And you want to do it cleanly. So if you do that and you're on AFSK RTTY, you want to be sure the other sideband, the lower sideband, doesn't come out. But that's true for voice too. And you want to be sure the carrier gets annihilated in the radio. The carrier should be subdued by 30, 40, 50 dB. So what you're transmitting is just DD, DD as 2 RF signals. At the other end, for someone listening to a RTTY contact, you can't hear the difference. You can't tell how I'm generating RTTY. So FSK and AFSK are, let's just say, nearly identical from the point of view of someone you're talking to. If you look at both on a spectrum analyzer, you can't tell which is which if the AFSK is sent cleanly and you're not overdriving the radio. But that's true of phone as well. So as they say, the automatic level control, the ALC in your radio ought to read 0 if you're transmitting RTTY. If you're on voice, yeah, you can give it a little bit more audio. So I found across this. Now, I'm not old enough to have ever played with these, but I worked some people say, oh, yeah, I use that in, somewhere. Teletype printers, really printers that would go click, 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 a typewriter. The early teletype came out as print on a screen. So another picture on the internet, about 1950, so a printer. Anyone know the name of that receiver? How about that transmitter? My favorite microphone, D104. I have like 10 of these behind me. I like to collect these. My wife draws them for me. She's the artist, and she drew some D104s that are just, they're more valuable than the actual D104. So this was a prime station in 1950 or so, sending RTTY. Now, by 1990 or so, the gadgets look like this. This is what my son used. PK232, an AEA. So this was called a terminal node controller, a TNC. And this talked to the radio by a radio cable, and this talked to the computer, or really any dumb terminal. Now, granted, this isn't a dumb terminal, but it's, by today's standards, pretty dumb. This controlled the print, so I type here. My son was typing here. The information went to here on one cable, and the information here went to the radio. Simple 1990 sideband ICOM radio. And he got on, his favorite mode was PACTOR, PACTOR 1 back then. Man, this worked well. Very, very efficient. So AFSK radio, if you look at the what's called the waterfall, it looks like this. Just two parallel tones. The tones are separated by some radio frequency. Traditionally, it's 170 hertz. In the older days, when radio receivers weren't so good, it was 450 hertz. In the really old days, some 800 hertz or something. So you've got to be able to distinguish the two tones. If I go back to RTTY, here's RTTY 45 baud, 170 shift. And here it is with a wider shift. It's still RTTY. Now the problem is, if the shift is 850 hertz, it would take up that much spectrum. That's kind of wasteful for sending a RTTY signal. So you don't hear that on the bands anymore. This was a program I bought in the 1990s, MMTTY. The author is Japanese, gave it away. MMTTY. What an amazing program. The specialty is RTTY, radio teletype. It could work by sending AFSK or FSK RTTY. And man, it had so many controls and things and filters. You know, it was really like opening the engine and messing with the fuel injection. But it worked really well and had these gorgeous images to know when you're tuned in properly and all. So RTTY. All right. So during a RTTY contest, I caught this with an SDRplay spectrum. Look at this. Wall to wall from 3560 to 3590 or so. Almost all of these are RTTY stations. But look down here. It's only a couple. Most of this is CW down here. But literally, during a RTTY contest, I hear the RTTY operators go all the way down to the bottom of the band. It's legal. It's not very friendly, but I see right here there's some spaces here. That tells me, there's a couple of FT8 signals here because they're all stopping at the same time. So RTTY is still popular, but I'd say only during a contest. So I wondered whether I should talk about this stuff because I don't want to get too deep into the weeds. What's a symbol? What's a baud? So symbols. What's a symbol? Da, dit, that's a symbol. So baud is just another way of saying something's changing per second. Now that's a buzzword, baud. It's a rate. If someone says what's the baud rate, it's like that's redundant. Baud is already a rate. Something's changing. The frequency, the phase, the amplitude, something's changing. So the baud rate is the symbol rate if there's just two possibilities. Currently on HF, we're restricted to 300 baud. That's a legal thing in US. A lot of the debate now is, why don't we drop that and just say, hey, why don't we have a bandwidth rate? That's another hour talk. Not going to do that. But it's kind of an interesting argument among the digital operators. Baud in words per minute. There's no one-to-one here. So CW, 20 baud, 24 words a minute. PSK 31, 30 baud, 50 words a minute. Hey, that's twice this. Wait a minute, what's going on here? Well, it must be more efficient, right? RTTY 45, 45 baud, 60 words a minute. So you see, there's no one-to-one correlation here between baud and words per minute. It depends on how the structure is set up. Olivia is very popular on the HF bands, 63 baud, only 30 words a minute. That's why it also works to very, very faint levels. It's like, increasing the hearing there. 8 PSK 1000F. That would not be legal on the HF bands, 1000 baud. But it is legal on 2 meter FM, 440 FM. 3,000 words a minute. I can't talk that fast. So this is what we use in the county emergency drills with little simple sound cards and a little simple FM radio. Even if we go in the mic jack, 8 PSK 1000F. The audio is the same audio for a human voice. In fact, it's a little more restricted. So it transmits information at gazillion times faster than I can, talk. So we use this to send spreadsheets, emergency communications of all kinds. All right, so I thought, how do I explain multi-frequency shift keying? I thought, it's easy. We're going to look at music. If you ever play a bugle or hear a bugle, da, 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 it can only play a few notes. Musically, they're called thirds and fifths. That doesn't matter. But there's only a limited number of notes, and you've got to mess with your lip to play the different notes. Da, 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 da. That's it. but you mess around with, which is first. Trumpet's the same instrument, except it has these valves. What do the valves do? Da 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 da. You can play all 12 notes of a chromatic scale on a trumpet. I can't, but I mean trumpet players can. What do the valves do? Well, look at how the trumpet's built. It's changing the length here of the tubing. So what you're doing by changing the length is you're changing literally the wavelength. Well, it's just like an antenna, right? Changing the wavelength, the longer the wave, the lower the pitch, just like an antenna. So that means what? With a trumpet, I can play more information per second than I can with a bugle, right? You get it? I thought that was a pretty cool analogy. Bugle and a trumpet. Da 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 da. So all these different modes are multiple tones. So per second, I can send more information. Does that make sense? That's kind of hard, How about the bandwidth? Well, I don't want to be too greedy. If I send on AM, that's about 6 kilohertz. Like, I don't want to do that. But I hear some AM on 80 meters, 75 meters. Those guys are amazing. They're the high fidelity nuts. 8, 10 kilohertz. Single sideband phone, 2 or 3 kilohertz. Look at that. CW, 100 hertz, 300 hertz maybe. PSK, only 50 hertz. That's amazing. How did he do that? You can get more conversations for a given band if we all said, let's just use PSK 31. So that's why it reigned the roost for, 30 years. Olivia, blah, 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 THOR, Vera. So obviously, the bandwidth is kind of important because we don't want to QRM each other, at least not on purpose. JT8, FT8s. I'm going to skip all my JT slides. Oh, so a couple days ago, June 9th, I listened for, about 5 minutes or so, 10 minutes on 20 meters. I often hear, someone says, 20 meters dead. I thought, what? So this was, what time of day? It was like 10 in the morning. Oh, 10 a.m. Everything here I heard with my radio. Do I have some big element beam? No, I've got a 17-foot wire lashed to a tree. That's my antenna on. Everything here I heard. Now, I didn't work them all, obviously, but so FT8's very, very effective for getting all over the world. Even when you think the band's dead, it's not. This is amazing, too. This is on which band? I think 20 meters. I'm not sure. But here's a 3 kilohertz audio passband. Everything here is a different tone, and I could hear it in speakers or headphones. What's amazing is FT8 can decode not 1, not 2, all of them at once. It's like, wow, how does it do that? It's like if I'm listening on CW at a contest and I hear like 5 signals, I can't figure out which pitch I want to concentrate on. FT8, the software that is, separates all these out and prints. This is what I just heard. So this is this. So in about 15 seconds, FT8, yeah, all these, CQs are in green. Anyway, you can see why FT8's so important. FT8 watering fall. This was my claim to fame. I thought, oh, I got up once. It was 40 meters. It was like 6 a.m. before it was in the winter. So I get on 40 meters. I hear VK3 LDB Australia calling CQ. I set my radio for 10 watts. My antenna's a wire in a tree, and I worked them. Look at this. That was so easy to do. In fact, it was kind of too easy. It was a thrill, and then I realized, well, the software is doing all the hard work, But look at that, a contact with Australia with a couple of watts on 40 meters. FT8. So what can I do with more tones? I can send more information per second. How's that work? May represent different combinations of zeros and ones. So if I sent the Gettysburg Address, that's my standard file, by all these different modes here, this is how long it takes. The same file, 4 minutes, 30 seconds. These are all possible with sound cards and a simple radio. OFDM is kind of a new mode. THOR, MFSK, multiple carriers. I'm going to skip these. Here's what MFSK 32 looks like as a spectrum. Kind of pretty down here, but it's about 600 hertz wide. So it's a little wider than a typical CW signal. Oh, here's my grandson a couple years ago. So I sent this message on 2 meters FM using the mode MFSK 128, send an image. And the way it sends it, it goes deedly, 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 just like a fax machine. And it paints the picture literally, red, green, blue, red, green, blue. The software puts it together, and bing, you got a picture. That's fun. Olivia, amazing mode. It can work well below what I can hear in headphones. This is what the spectrum of Olivia looks like. Very sharp. Meaning there's not a lot of sideband information. About 500 hertz. THOR, my favorite. THOR. Here's the spectrum of THOR. THOR is also nice because it's not the tone, that's the symbol. Wait a minute, I said it's frequency modulated. If you go D, D, the software figures out the change in pitch. That's the symbol. So THOR uses what's called incremental frequency shift keying. That's amazing. What does that mean? It means my radio can be drifting, or I can do this with the VFO and I still get perfect print. In other words, you can use THOR 22 on a 50-year-old tube-type radio. It still works fine. PSK. PSK is harder to describe. I'm changing the phase of the wave. Phase is the timing. So in phase, 0 means no phase shift or a phase shift, and 1 means a phase shift or a no phase shift. Notice I'm not changing the amplitude. I'm not changing the frequency. I'm just changing the start and stop, the phase of the wave. That's much harder to visualize or hear. Here's what PSK 31 looks like if you were looking at this on an oscilloscope. The wave does collapse, grows, stays, and then collapses. At the collapse point right here, if you look closely, the phase just changed. 180 degrees. So why do they do this? I wrote to the author and said, I don't get it. Why do you have to change the amplitude? So he said, it's simple. I want to keep the bandwidth narrow. What if I change the phase when the wave was at its peak? Then you generate all kinds of harmonics and it would take up a lot more spectrum. I get it. PSK 31. Here's what it looks like on a waterfall. Very narrow. Here's what it looks like on a nice spectrum analyzer. Look at these two peaks. That's the 31 baud. 31 baud, it's like a square wave. Back and forth. That's why it sounds kind of terrible musically. Here are the harmonics. 10, 20, 30, 40 dB fainter. You're not going to hear the harmonics. I came up with this. Okay. C phase. I've got 2 flags, right? I only have 2 flags, but look at all the information I can send by doing what? Just moving the flags to a different phase, a different position. So if someone says, I don't get, how does PSK 31? I'd start with this. Here's how this works, you know, the semaphore thing. So with 2 flags, I can send different letters, numbers. So I'm altering what? The position. That's the phase. So 1 phase shift carrier. How about multiple ones? Can I send, instead of 1 phase shift, 5, 10, 20? Here's what that would look like. So PSK modulation can be multiple. Now, why is this better? Well, I can send more information per second. Granted, I need more bandwidth, but that's always true. If you want more information per second, you need more bandwidth. Let me see if there's anything else interesting.